how do they get the cat's eye into the marble? What exactly goes inside a water filter? How do they build a toolbox that's military tough? And how did this machine revolutionize packing foam? Find out next on Factory Made. It's been the cat's meow of marbles ever since it was first invented back in 1950. The cat's eye marble is prized for its swirling ribbons of colored glass that kind of look like a cat's eye. To get one, you could take up trading or shoot one off an opponent. But to get the cat's eye inside the marble, you really have to know your glass. Given how treasured the cat's eye is, it's kind of surprising that it and lots of other marbles are made from trash. In this case, recycled glass. It comes from all kinds of stuff, like perfume bottles, beer bottles, and even decorative pebbles or knickknacks that never sold. To make a cat's eye, you start with clear glass for the body of the marble and melt it by the bucket load in a large, deep crucible inside a furnace. Over 10 hours, the furnace heats the glass to exactly 2,300 degrees Fahrenheit. The temperature has to be just right. If it's any cooler, the glass is too thick to flow. And any hotter, and it's too thin and runny to cut into marbles. It's not until the clear glass reaches just the right molten consistency that the colored glass for the cat's eye finally goes in. For this batch, they're using some discarded glass pebbles. And to form a cat's eye, the blue pebbles have to be placed exactly in the center of the pool of clear hot glass inside the furnace. The blue glass melts almost instantly on contact and drops straight down through the clear molten glass like a shot of grenadine in a tequila sunrise. They don't stir it, so the blue glass stays centered within the clear glass. And that's how they get the blue glass inside the clear glass. Then the whole batch flows out of the furnace to be cut up by a heat-resistant carbon blade into individual marble-sized chunks called slugs. The slugs fall into iron cups that drop them into the forming machine, which is made up of giant coils that roll them into marbles. Each slug lands on a groove between two of the coils that tumble the slugs into perfect little spheres. The two colors of glass don't blend together as the marbles tumble. That's because glass cools from the outside in. So the two colors quickly form outer skins that keep them separate. But it's still fluid enough that the constant tumbling causes the blue ribbon to swirl around in the clear glass. And that's what creates the distinctive cat's eye pattern. Look closely. The more the glass cools, the easier it is to see the swirling cat's eye within the clear glass. After just 60 seconds in the forming machine, the marbles have dropped in temperature a full 1,000 degrees. Their pattern is set, and they're firm enough to travel down a ramp and drop into buckets. But get this, even though they're cooled off a lot, the marbles are still hot enough to ignite a piece of paper. It takes a full 24 hours for the marbles to completely cool. The whole time, they cool from the outside in. That's why they keep their shape and don't stick together in the bucket. And if they cool too fast, the hot inner core of the marble expands and cracks like the marble on the right. Once they're cool enough to touch, a worker sorts the marbles for cracks chips, and flaws. Then, the blue cat's eyes pour into a machine that packages them with other colors. So you'll have an assortment in every bag. And in just a day and a half, the cat's eye went from trash to treasure. This simple canister can trap dangerous chemicals, bacteria, molds, and other nasty things. When installed under a sink, a water filter like this cleans tap water by filtering out particles and contaminants. The shiny silver canister holds it all together. But it's the stuff inside the canister that's doing all the work. To make a water filter, you first have to make the canister. And believe it or not, the tall, narrow canisters actually start out as flat aluminum discs that get shaped and stretched inside a machine called, what else? A can maker. First, a hydraulic ram presses each disc into a cup-shaped die. Then, the disc pops out of the die, reshaped into a little cup. Here comes the ram again, bearing down on one of the discs in the die. It takes 2,000 pounds of pressure to reshape the disc into a cup. A clamp grabs the cup and places it on the end of another hydraulic ram. Then, the second ram pushes the cup through several round openings, each one slightly narrower than the last. Squeezing through the narrow openings forces the aluminum to thin and stretch. As the cup becomes taller and taller, until the cup is stretched into a 10-inch canister. Finally, a blade cuts the canister to size. And a press adds the dimples and rims that hold on the water filter cap. When the canisters are finished, an industrial-strength washing machine gives them a good scrubbing to remove the coolant, grease, and other contaminants that could have been picked up inside the can maker. Then, the canisters are loaded onto a rotary table that heats them up to 580 degrees and spins them past sprayers that coat the insides of the canisters with a plastic coating. Once it's baked on, the coating protects the canisters from rusting. And it prevents contaminants in the aluminum from leaching into the drinking water. After passing through an oven, the canisters shoot out into a quenching bath to cool off. This cures the plastic coating, guaranteeing the drinking water never comes in contact with the aluminum surface of the canister. The canisters are now ready to be filled with the filtration materials. They include a bundle of plastic-based filtration fabric that sits on top of some black powder, which is activated carbon or a byproduct of superheated coal. The carbon goes into the canister first. It's extremely clean, porous, and absorbent. And it acts like a magnet for toxins, sucking out the bad stuff and letting the fresh water flow through. The plastic-based fabric comes in huge rolls. A machine cuts down the rolls and heat seals a half-dozen layers of fabric together to make a single filter. Another machine folds the layered fabric into an accordion shape so it will fit inside the canister. A machine attaches a cap to each fabric filter, and a worker places one filter in each carbon-filled canister. A press forces the cap down into the canister. And a rollover machine crimps the metal lip around the cap for an airtight seal. The cap has to go on tightly like this to be sure outside contaminants don't find their way into the filter. The cap gets a quick lube job, the final protection against leakage. Then all that stuff that went into the filter is ready to catch particles in your water that are just 1/100th the width of a human hair. This toolbox is on a mission to arm U.S. forces with the tools they need to fix military equipment wherever they're deployed. So it has to be rugged enough for combat, but also light enough to pack up and go. And this toolbox is able to fulfill its mission thanks to its tough outer shell and even tougher testing. The toughness of the toolbox comes from a special blend of plastic pellets that together is stronger than any single kind of plastic. The multicolored bits are a mix of recycled plastics, and the black pellets are added for color. But the most important plastic in the mix is the white polypropylene. This is an exceptionally rugged type of plastic that can withstand extreme temperatures and major impacts, like being dropped from a helicopter. A vacuum sucks the pellets into a melting barrel that's heated to 400 degrees, where a special foam mixes with the pellets as it melts. The foam itself is a secret material, but we can tell you that it creates small air pockets within the molten plastic. This makes the plastic lighter in weight while maintaining its strength. To form the melted plastic into the base of the toolbox, a hoist loads a huge 10-ton mold into an injection molding machine. Believe it or not, this giant mold is for just one toolbox base. It's so big because it has a lot of hydraulic and cooling hoses built into it for the injection system. And so that the metal is thick enough and strong enough to be pressed shut so the molten plastic doesn't seep out. To fill the mold, a hose attaches to it to pump in the plastic. And a hydraulic pump drives a giant screw that forces the liquid plastic through the hose and into the mold with 1,100 tons of pressure. It takes 20 pounds of liquid plastic to completely fill the cavity for the toolbox base. Then, cool water flows through the blue hoses on the mold to completely harden and toughen the plastic. When the plastic is set, ejector pins push the base out of the mold, and a robotic arm uses suction cups to lift the base out of the machine for assembly. A worker uses stainless steel hinge pins to attach sturdy plastic handles to the base and 2-inch thick polyurethane wheels to the back. They'll make it easier to roll the toolbox over rocky terrain. The same thick steel hinge pins attach the lid to the base. When the lid is open, it's designed to function as a workspace. And the hinge is so strong, it can support up to 50 pounds. A polymer seal, or O-ring, lines the inside of the lid to make the box watertight and airtight when it's closed. The seal works so well, the lid needs a special pressure valve so the lid can be easily reopened. But before the toolbox makes it to a military base, it takes a beating. The toolbox is dunked in 3 feet of water for about 30 minutes to be sure it's airtight and waterproof. The drop test determines how tough a fully loaded box is when dropped from 3 feet. to simulate a tumble off a transport truck. And finally, a pointed 25-pound steel weight is dropped from 3 feet onto the lid to make sure the toolbox is tough enough to take almost anything that might come its way. Packing foam, like this egg crate foam, this custom toolbox insert, and even this special static-free foam, makes a good cushion because it's so soft. But surprisingly, that same softness makes foam like this extremely difficult to cut. More difficult, in fact, than stone or steel. That's because the soft foam collapses or gives when pressed by a knife or blade. So the only way to cut it is to put enough pressure or force behind the blade to cut through the give. To make the egg crate foam, the huge block has to be cut down to size, and it weighs about 225 pounds. That's why it takes a massive computer-controlled bandsaw to cut a huge block of soft, squishy polyurethane foam into the thin slices that make egg crate foam, like the kind you can use as camping pads or as padding inside equipment cases. The sheer size of the block cuts back on the natural give in the soft foam, which could jam the blade. And the saw uses an ultra-sharp serrated steel blade that's mounted in the cutting head with so much tension, it stays perfectly rigid even as it sinks into the foam. Without the tension in the blade, the serrated edge wouldn't be able to glide through the foam and cut it like this without getting caught. When the saw is finished, the large block is cut into 2 smaller blocks with the exact contours or shape of the finished egg crate packing foam. But it takes a second saw to slice the blocks to the proper thickness. The tension on this steel cutting blade is set to 15,000 pounds per square inch, which is tight enough to prevent the blade from sinking into the foam. The cutting table moves back and forth, rather than the blade, to ease the foam past the rapidly rotating blade. The cutting head drops with each pass until both blocks are cut into uniform slices. But without this machine, the egg crate texture of the foam would not be possible. The machine, called a convoluter, automatically slices the foam into 2 interlocking pieces of egg crate foam that look a little like the mouth of an alligator as they come out of the machine. The secret to creating the teeth-like texture is the interlocking spikes on these 2 rotating drums. The spikes press down on the foam right before it passes by a horizontal cutting blade inside the machine. The compression of each spike forces more of the foam past the cutting blade, creating the valleys in the egg crate pattern. The spaces between the spikes are cut less, and that creates the cones. This egg crate pattern is actually better at cushioning fragile stuff than flat foam, because the tip of each cone acts as a little shock absorber that diffuses any impact through the base of the cone. But it takes another kind of foam to package and protect computer hard drives and other electronics during shipping. Media foam, as it's called, has to be static-free, because static electricity can erase hard drives or hurt home electronics. This This media foam is made from cornstarch, which is naturally static-free and 100% biodegradable. But it's also so soft, it takes a mechanical press and 115 tons of pressure to punch through the give in the foam to cut through it. Once cut, the foam snaps apart to create a static-free custom fit around any electrical component. However, for a custom-cut toolbox insert, a flatter, denser foam like this sheet of polyethylene is best. A computer determines the most efficient layout for the tools. And a high-density ceramic blade does the cutting. This type of ceramic blade is strong enough to cut through some of the toughest metals. So it's able to power through the foam without snapping. The foam itself is so strong that even after it's cut, it holds its shape without tearing or stretching. Which means it could last as long as the steel tools it cradles and protects inside a toolbox.